Welcome to qnawire.
Would be the diagram of the system, and we know that we're going to consider charge on a length of the cylinder. This can be expressed by the charge equaling the linear charge density lambda times the length. But since the surface area we know to be equaling 2 pi r times L on a cylinder, this can also be expressed, Q can also be expressed as the surface charge density multiplied by 2 pi r L, or the surface charge density multiplied by the surface area. So these two expressions must equal to each other. Therefore, the surface charge density times the length must be equal, rather the linear charge density times the length must be equal to the surface charge density times 2 pi times r times L. And so we can then say that the linear charge density lambda would be equal to 2 pi times r times the surface charge density. We're going to apply then Gauss's law to a Gaussian surface that is a cylinder of length L, radius lowercase r. So we can say Gaussian surface, we can say cylinder. And here we have a length L, radius r. And we're going to then say that the charge enclosed would be equaling the surface charge density multiplied by 2 pi times r times L. And we can then say that the electric flux is going to be equal to 2 pi r times L multiplied by the electric field. And so we know that due to Gauss's law, the electric flux is going to be equaling to the charge enclosed multiplied by epsilon naught, the permittivity in a vacuum. And so we can say 2 pi r times the length times the electric field is going to be equaling the surface charge density multiplied by 2 pi r times L. And this would be divided by, again, epsilon naught. And so we find that E, the electric field, is going to be equaling the surface charge density times r divided by epsilon naught times r. Capital R being the radius of the cylinder, and then lowercase r being the radius of the Gaussian surface. So this would be our answer for part A. This would be our answer for part B. And then finally for part C, they want us to simply evaluate from example 22.6. We know that the electric field of an inch line of charge, we find that E is going to be equaling the linear charge density divided by 2 pi times epsilon naught times r. And so the linear charge density, the surface charge density rather, is equaling lambda divided by 2 pi r. And that is simply from part A. And so the electric field would be equaling the surface charge density times r divided by epsilon naught times r, and this is equaling r divided by epsilon naught times r multiplied by the linear charge density divided by 2 pi r. And so the electric field is equaling the linear charge density divided by 2 pi epsilon naught times r. As we can see, this is going to be equal to the equation that we example 22.6. This is the same as for an infinite line of charge that is along the axis of the cylinder. So this would be our answer for part C. That is the end of the solution. Thank you for watching.